Quantum Computing for Financial Models by Nicholas Hook. The problem: calibrating parameters of the financial model, called Black-Scholes, requires solving nonlinear optimization problems, and these are sensitive to noise and initialization. There are classical methods, like the Monte Carlo simulation and the gradient optimization, but these are slow and scale poorly for high-dimensional models. This research will explore whether quantum-inspired optimization of Black-Scholes, specifically imaginary time evolution, can improve stability and convergence. Related work. These are non-imaginary time evolution quantum methods. The most famous existing quantum approaches include quantum annealing. Here, we reformulate financial optimizations as ground state searches of Ising Hamiltonians. Quantum Monte Carlo integration speeds up stochastic simulations for pricing and risk analysis. And then there's quantum machine learning, which can be used to detect market patterns. The limitations of these already established methods is high noise sensitivity and current hardware constraints. These are also focused mainly on combinatorial optimization and not suitable for something like the Black-Scholes model, which is continuous parameter calibration. Here's related works for quantum imaginary time evolution methods. What's the principle behind imaginary time evolution? We replace time, t, with imaginary time, which is it. The evolving system tends towards its lowest energy state, and this will correspond with an optimal solution. It transforms the Schrödinger equation into a diffusion-like process that smooths convergence. Here are some key developments in imaginary time evolution. The first is variational. This is shallow circuit combination of quantum and classical that uses parameter updates. We have quantum imaginary time evolution, which is local unitary approximations with linear scaling and high-dimensional efficiency. And we have deterministic weak measurement approaches, which are suitable for noisy devices. Project positioning. The gap in research is that imaginary time evolution has rarely been applied to financial model calibration, even though it has great stability and determinism, both of which are needed for calibration. The research objective is to implement an imaginary time evolution-based optimization routine, which will calibrate Black-Scholes parameters. The results will then compare against classical methods. The expected outcome is a smoother convergence under noisy conditions, and a demonstration of quantum-inspired benefits without requiring full quantum hardware, as well as a framework for extending imaginary time evolution to broader financial optimization tasks. In conclusion, quantum computing offers new routines for financial optimization beyond established ones like the Monte Carlo. Imaginary time evolution provides deterministic and physically motivated approach to finding the ground states, which correspond to optimal parameters. My project bridges physics and finance, bringing quantum techniques to practical modern model calibration. Future work after the research will include extending imaginary time evolution to other financial tasks like portfolio risk minimization. Thank you.